what are the basic characteristics of the geomaterials which are required to define its sorption and desorption characteristics. Basically, it is an excellent philosophy to simulate geomaterial contaminant interaction. As I said, though they are in opposite mechanisms, these are the strategies which are normally used for remediation of contaminated soils and the geomaterials. This comes under the category of site cleanup and site remediation program, and there are several types of strategies for remediation of contaminated soils. The first one is soil washing. Alright, you inject fresh water into the soils which are contaminated, and then we presume that desorption process will occur. The contaminants will get released from the substrate, they will flush out in the pore fluid, and this pore fluid can be sucked out later on. Is this okay? This is what you have been asking. So, the more and more water you add to the system, you are diluting things, at the same time you are creating a situation where desorption initiates. Unfortunately, in today's world we do not have so much water. The second question is the amount of sludge which you are going to create, that becomes a secondary source of contamination, and then you have to do some special things to take care of the sludge which you have created. And then the question is volume, the question is intensity of the concentration, and the question is where to store it, how to neutralize it, where to dispose it. Soil flushing, I think similar thing, what we were talking about, the washing could be flushing also, fluids could be different. Vitrification, I think vitrification I had talked about some time back. At very high temperature, you take the soils which are contaminated, vitrify them. So, you must be coming across this word in the building industry, vitrified tiles, is it not? What are these vitrified tiles? You have taken clay particles, you have heated them at very high temperatures, clear, so that there is a amalgamation gets formed. Particles which were discrete have now become more uniform, amalgamated, vitrified. Cool it, it gains strength. This is a vitrification process. So, I can take the contaminated soils, I can use some plasma torches to create very high temperatures. I can vitrify the entire thing as if they melt and they solidify. Lava is a form of a vitrified material which is coming out of the volcanoes. That is a vitrification process. And when you cool the system, the chances are the surface might have vesicles because of the trapped airs, the trapped gases which are coming out of the volcanic eruption might come out slowly, and those vitrification thing might have vesicles formation also. But when you do it under controlled circumstances, the vesicular formation would not be. This is the process which is being used by the people or the industries which are producing extremely toxic waste, including the nuclear waste. So, one of the ways to get rid of the toxic nuclear waste is vitrify the contaminated soils, but very expensive. A lot of research has been done and should be done in Indian context, so that these techniques can be adopted. The question is, large amount of soils, the volumes are going to be so huge that how vitrification would be done and how the cost would be economized, time, efforts, this is the big question. Then is solidification. I might take contaminated soils, I might add a solidifier into it. Sometimes we also call these agents as stabilizers, immobilizers. Cement is a stabilizer cum immobilizer cum solidifier. So, if I take contaminated soils and if I mix cement into it, what I have done? I have trapped all the cations, unwanted species which were present in the system because of the cementation effect, clear. So, all these cations get held chemically in the matrix of the cement. Now, they cannot come out in the environment, you got this point. So, solidification is a good form of immobilizing the waste. Now, this solidification could be achieved by several activities. So, one example I have given you is adding cementitious materials. Another way would be lower the temperatures and freeze the entire thing. So, if I change the state of the material to a frozen state, what ice does? Ice will also interlock all these contaminants in such a manner in its matrix that they cannot come out unless the system melts. So, are you getting the point? I mean, these are the concepts which you can use for decontamination of or the remediation of the contaminated lands. Immobilization, I think I have already given you an idea about immobilization. You are immobilizing the movement of the cations in a porous media. It could be a chemical process, it could be a physico-chemical process, it could be a physical process like lowering down the temperature. What about the pressures? If I enhance the pressure, the interlocking is going to be better. All right. So, I can use different techniques to immobilize the waste which is migrating into the porous media. Is this fine? Now, under all these circumstances, you have to study the activity of the contaminants and the porous media or the geomaterials, and this is where you have to characterize the geomaterials to study their sorption-desorption capacities. Is this okay? Any question? I have given you a lot of ideas and a lot of thoughts.
So in case of vitrification process, we get all the contaminants on the surface only after completing the
no, this could be in situ. So, suppose if I know the place where the soil is contaminated, what I have to do is I have to just maybe insert the plasma torches and the whole system can be vitrified in situ itself.
we get all the contaminants on the surface of that particular.
Not surface, within the matrix also. Yeah, because the whole idea is to do a sort of a melting of the sand particles or the clay particles.
Yeah, if the contaminants are inside the matrix and after
so they get trapped there because of the elevated temperature. So, plasma torches normally work at the temperature of 1400 to 2000 degrees centigrade. That is what. So, what you have done under in situ condition itself, you have frozen the entire thing. This I could have done by injecting cement or some binding material and then waiting for some time to matrix getting formed. You are getting this point?
After that, that place is immobilized like a concrete floor it is.
Exactly. So, when the extent of contamination is too much, the best way would be vitrification, but very expensive. Second would be immobilization or solidification. Make things immobilized. But you will be surprised to know that not much research is being done here. Now, this is a subject which interfaces with metallurgical engineering and material sciences. Why? So, sometimes when you get chance to go through the nuclear power stations or research stations or watch it on YouTube, what they do is they take glass, and normally glass is used to vitrify the entire thing. So, they encapsulate the atomic waste in glass. Fine. Why glass? Amorphous system, impervious, nothing can come out of it. Remember the salt domes which we have talked about? So, salt domes are these creations of the nature, best places to dump your atomic waste, nothing will come out of it.
Sir, in this immobilization, like we are immobilizing that contaminants, right? We are not actually removing.
No, we are not removing.
So, what is?
Why? The reason is concentrations are too high. See, remember, even if I take out something from some phase, the next question is what I am going to do with this? Where I am going to keep it? So, it is something like cancerous cells have been removed the body, but now the question is what to do with it. So, what hospitals do? They incinerate it immediately, they can't store it. Are you getting my point? So, the more and more you take out the toxicity from a system, you have to handle it, you have to store it, clear? You have to manage it, and still the question is what should I do with this? This is what industry is asking you. I hope now you are getting at the crux of the problem. And another question is, should we stop the industrial activities? Should we become economically slave to other nations, because each and everything has to be imported then? And then also there is a problem, because everything will come in wrappers and the covers, and then ultimately what you will be doing? All these wrappers, covers and the packaging waste would be going in the landfills. So, the cycle is vicious. So, importance of sorption and desorption characteristics. In several fields of environmental geomechanics, these concepts are being used. Number 1, fate and transport of contaminants. Why contaminants should migrate from one point to another point, clear? I hope now you can get the issue easily. If sorption capacity is extremely high of the substrates, they will not let cationic species to move from one point to another point. This could be good, at the same time this could be bad also. So, when you are inserting permeable reactive barriers in the ground, you are creating a very activated system which is bound to attract most of the cations and give you fresh water downstream. But in the due course of the time, the filter itself is getting contaminated and becomes a big source of contamination. Now, what you are going to do? Take them out, wash them and again insert them, or design a system which is going to last for 50 years. This is the scope of environmental geomechanics. I hope you are realizing that these are the questions which have been ignored completely. Not many people have tried to answer these questions. So, these technologies have to be developed in-house. We should not be dependent on others, because these are basic simple concepts. Anybody can design such systems. Efficiency of environmental cleanup strategies. I think now you can understand why sorption-desorption mechanisms are important. If I have to show that after encapsulation, alright, nothing moves out from the matrix in the form of cationic suspensions or cationic solutions, my immobilization is the best one. So, I have immobilized the waste to an extent where even after it comes in contact with water, nothing leaches out, clear? A simple cleanup strategy which you have created. Imagine, see, this is the beauty of these sentences, that their implications are so tremendous. So, you have a landfill and surround the entire landfill with some curtains which are not cutting off the seepage only, but they are reactive also. So, curtains which were done by grouting were only stopping the seepage, clear? Now, what you have done in the form of reactive barriers, you are treating the contaminant and stopping their movement outside in the geo environment. So, selection of suitable geological formation and backfill materials which can be utilized for going ahead with your disposal programs, alright. So, Government of India requires these type of studies to be done, in a very vigorous form, because they have to select the sites where the waste should be dumped. Similarly, the backfill material, you remember we were talking about the backfill materials required for stopping the contact between the containers of the waste canisters we had talked about and the environment. So, what type of backfill material should be utilized so that they are the best sorbents? They will not let even any radioactivity to leach out in the environment, either in the gaseous form or in the liquid form. That is the isolation of the waste. Design of barriers, I think we have discussed enough of the waste containment system, accumulation of heavy metals and pesticides in subsoils. So, soils which are heavily contaminated because of fertilization, because of insecticides which are being used in agricultural practices, they have to be decontaminated. I think I gave you one good example in the beginning of the course. In most of the parts of Punjab, Haryana, the soils are heavily contaminated. So, how would you decontaminate them? Create a strategy. So, you will be the number one consultant in this subject. The soils have become contaminated because of various agricultural activities, over fertilization, and all those chemicals are still remaining in that root zone. So, fertility is lost, alright, and what you have done is you have made them as a secondary tertiary source of contaminants. So, every time when water interaction takes place in the form of rainfall or the flooding, there is a problem to the groundwater. So, what are the challenges? It is easy to list all these things. The challenges are that precise determination of KD itself is a big question mark. We are using this parameter to define the interaction between contaminant and geomaterials, alright. But now what I am saying is that determination of KD is tough. The way I have written here KDL corresponds to KD parameter associated with the leaching process, desorption process. So, KD is the sorption process and KDL is the leaching or the desorption process. Very soon you will realize that it is quite difficult to measure KD and KDL precisely, but we should still try. As an engineer, I want some numbers, is it not? Without numbers, I can't design my systems. I can't dispose the waste, particularly toxic waste like nuclear waste. Okay, so little bit about the KD parameter, though I gave you the background of what KD parameter is basically a sort of a distribution taking place. In case of geometry, this could be clay particles. So, as if the clay particles are lying over there and the flow of contaminant was taking place in a fluid phase, and then suddenly something which is of high surface area, high cation exchange capacity, high chemical activity comes, and the moment these guys realize what is going to happen, all of them will get distributed from this stream and they will get parked over there. This is the KD process conceptually. Hope you have understood now. Is this okay? Now, what we have to do is we have to just find out how much fraction of the contaminants have left the mainstream flow, and that can be related with the activity of the substrate. Clear? So, whatever percentage fraction of the contaminants are getting parked on the substrate divided by whatever is in the fluid phase would be a ratio which is nothing but KD. So, now let us see how to define this, alright, in a copybook manner. So, this is also known as the partitioning or distribution coefficient. This is a measure of sorption of contaminants to soils, rocks, admixtures, geomaterials. Would you consider bacteria as a geomaterial or not is a big question. Bacteria in the soil matrix is a geomaterial. Why? It provides a surface, and I am sure that what Shashank has done is he has started working on biosorption. Clear? So, the sorption which is having because of or which is getting induced because of the bioactivities. And what are the bioactivities? MICP, microbially induced calcite precipitation. So, inside the soil you have created a system which is still very active because of the presence of calcium, and you have created a phase at which the interaction with contaminants might occur. So, remember my example Multani Mitti, the one which you use for your facials, bentonite, activated clays, pour it in suspension, add some sandalwood powder, turmeric powder, all these materials are good substrates. What they are going to absorb? Bacteria, sweat, salts from your skin. So, the moment you have a substrate which is charged, active chemically, mineralogically, the species which is getting parked over this is going to create a partition phenomena. You can find out the KD parameter of skin and sweat, because nowadays everybody is talking about artificial skins. Is this correct or not? So, how would you grow skins if skin is not contributing to the filtering of the sweats? Point to remember. So, suppose if I define the concentration of the contaminants, in the solid phase, parked on the solid phase to the liquid phase, we normally define this as the ratio of the quantity of the sorbate sorbed per unit mass of the solids to the amount of the sorbate remaining in the solution, and this is what we define this as CS by CW. So, the reverse process is true for the desorption, and what are the issues related? I will come back to this definition of KD slightly later. The issues are the experimental conditions have to be controlled, particularly temperature and pressure, because KD is very susceptible to the pressure temperature conditions. I think we have discussed this. Why temperature? Because the rheology of the fluid is going to change because of temperature, and pressure is going to affect the bonding between the contaminants and the surface on which the system is going to work. Measurement methodology itself is a big factor which contributes to the whole thing, because there are several techniques of finding out the KD parameter. We will discuss some of them, and human errors, alright, the type of contaminants which you are using, whether they are active, whether they are passive, the concentration itself, and so on. The type of sorbent which you are using, that is the particle size or its geometry, because particle size and their geometry and the geochemistry are going to contribute to the mineralogy and its surface area and indirectly cation exchange capacity. So, to me it appears that KD parameter is the best way to characterize clays. Why? It incorporates into it the effect of environment also. Your liquid limit and sensitivity parameters which you have used to characterize clays are not complete, because they are not defining or imbibing in them how the clay particles are going to react with the atmosphere, environment. I think we have discussed this thing, type of substrate and type of contaminants and their concentration and all those things.